Have you ever wondered how we find the absolute best solution to a problem? Like the most efficient shipping route, the most accurate AI model, or just the lowest possible cost for a project? Well, in the world of math and computer science, it all boils down to one incredibly powerful idea: optimization. It's this quest to find the lowest possible point of a function.
So, here's how we're going to break it all down. First, we'll get a handle on what optimization really is. Then, we'll dive into our first big tool, finding something called stationary points. From there, we'll figure out if those points are a minimum, a maximum, or something else. We'll also see what happens when you have to play by certain rules. That's constrained optimization. And finally, we'll talk about convexity, which is basically the secret weapon that makes everything way, way easier.
All right, first up, what is all this optimization stuff anyway? At its very core, it's really just a quest to find the lowest possible point. That's it.
To get a feel for this, imagine you're dropped in the middle of a huge hilly landscape. Your whole mission is to find the lowest valley in the entire area. So, where do you start? You can't see everything at once, right? It's a huge challenge. And that's exactly the puzzle that optimization tries to solve. Now in math, we don't call it a landscape, we call it an objective function. And our goal is to find its minimum. And believe me, this is not just some abstract math puzzle. This is the absolute bedrock of machine learning, where you're trying to minimize errors. It's key in economics for minimizing costs, and it's all over engineering for maximizing efficiency. It's everywhere.
So how do we actually find that lowest point without wandering around and checking every single spot? Well, our first and maybe most important tool is all about looking for flat ground. Just take a look at this curve. You can see how it flattens out in a few places, right? It's pretty intuitive. We just know that the very bottom of a valley or the tippy top of a hill has to be flat. The slope is 0. So our strategy is to find all of those flat spots first.
In calculus, we have a name for these flat spots. They're called stationary points. A stationary point is simply any place on our function where the slope, what we call the first derivative, is exactly 0. This is our starting signal. It's where we begin our search.
And the great news is, finding these points is actually a pretty simple 3-step recipe. First, you find the derivative of your function. Second, you just set that derivative equal to 0. And third, you solve for x. And boom! The answers you get are all of your stationary points. They're your complete list of candidates for a minimum or a maximum.
Okay, but here's the plot twist. Just because you found a patch of flat ground doesn't automatically mean you're at the bottom. A stationary point is just a candidate because, well, flat ground can show up in a few different places.
And you can see the challenge right here. On the left, we've got a local minimum. It's like a bowl or a valley. On the right, a local maximum, like the top of a hill. Both of them have a flat spot right in the middle. Our first test finds them both. So the big question is, how on earth do we tell them apart?
And to make things even weirder, especially in more dimensions, you get this thing, a saddle point. Think of a Pringles chip or a horse's saddle. It's flat right in the middle, but it curves up in one direction and down in another. It's definitely a stationary point, but it's not a minimum or a maximum. It's a trickster.
So how do we tell all these apart? We pull out another tool, the second derivative. You can think of this as a curvature detector. It tells us how the function is bending at that flat spot. If the second derivative is positive, the curve is bending upwards, like a smile or a bowl. That's our local minimum. If it's negative, it's bending downwards, like a frown or a hill. That's a local maximum. And if it's 0, well, the test is inconclusive.
Okay, so now we can find and classify these flat spots. But what happens when our search has rules? What if we're not allowed to just wander across the entire landscape? This brings us to a really important idea: constraints.
So some problems are unconstrained. That means search everywhere. The area you're allowed to look in, the feasible set, is the entire space. But honestly, most real-world problems are constrained. This is like being told to find the lowest point, but you have to stay inside a fenced-in yard. Suddenly, the lowest point might not be a flat spot at all. It could be right up against the fence.
And these rules usually come in 2 flavors. You've got equality constraints, which means you have to stay exactly on a certain path. Then there are inequality constraints, where you have to stay inside a certain region. These rules are super important because they define our search area. And honestly, dealing with them can get pretty complicated, which kind of makes you wonder, isn't there an easier way to do this?
Well, as it turns out, there is. There's a special property that can make all of these headaches just melt away. It's called convexity, and you can pretty much think of it as easy mode for optimization.
This right here is what a convex function looks like. It's just one single perfect bowl. There are no other little valleys to get trapped in, no tricky hilltops, no saddle points to fool you. It's the absolute ideal landscape for our search because it's so beautifully simple.
And this beautiful simplicity gives us an almost magical advantage. For any convex function, if you find a local minimum, you have also found the global minimum, period. Once you hit the bottom of any valley, you can stop looking because you found the lowest point in the entire universe of that function.
This makes things so much easier. For these special convex problems, the global minimum, the local minimum, and the stationary points are all the exact same thing. This means our simple little three-step process from the beginning is all we need. Find a spot where the derivative is 0, and you're done. You've solved it.
So, look at how far we've come. We started by just looking for flat ground. Then we figured out how to classify it, and finally, we found this incredible property of convexity that just simplifies everything. We've basically built a toolkit for finding the best answer. And that's the big takeaway here. This ability to mathematically find the most optimal solution is a superpower. So I'll just leave you with this thought. Now that you have this power, what real-world problems are you ready to solve?